Okay, so now we're going to carry on with our discussion about limits. I think we'll probably finish tonight. This is chapter one. When chapter one is done, then we can move on to derivatives in chapter two. And I think I mentioned this the other day. Derivatives, probably the most important topic in all of calculus, but we'll get to that in a bit. So right now we have to finish up where we left off. We started to look at this notion of properties of continuity. And so keep in mind, what does it mean to be continuous? It just basically means that just in a very informal way. There are no breaks in the graph. It's just you can draw it without taking your pen off the paper, so to speak. So anyway, for continuous functions, if we're assuming that B is just any real number, F and G are two continuous functions, at least at the point x equals C. We don't care what's going on elsewhere, but at that one point, they are continuous. And by the way, let me just draw a little picture here so we can visualize this. And they could have any relationship to each other. It doesn't really matter. I don't know. Let's say something like this. Here's f of x, and here's g of x. And then they're both continuous at x equals c. And the properties that they give us are, um, now remember, b is a constant. So that means that we could, for example, simply multiply f of x by a constant b, and it will still be continuous. So we're assuming that they're continuous. Then multiplying one of them by a constant will means that it's still continuous. Okay. Number two, their sum is continuous. Three, their difference is continuous. Four, their product is continuous. Okay, five, the quotient is, and five, the quotient is continuous. Of course, that implies that we may not allow g of x to be zero. We'll just add that at the bottom here. Okay. Now, in this case, since we're assuming that this continuity occurs at point C, they're writing it as a g of C. But we can write it just in general terms, g of x is not going to be zero when we have a ratio like this anyway. So anyway, so therefore, each of these is continuous at every point in its domain. Now, these are functions that have a domain equal to the entire real number line. Oh, and here's another one. The composite function is continuous too. They saved that one for last, I guess. Okay. So tan of x. Now we know that the tangent of x has quite a few asymptotes because if you remember from a previous session, the tangent of x is equal to the sine of x over the cosine of x. So anywhere that the cosine equals zero, there'll be a asymptote on the graph of the tangent of x. And in fact, if we go back to Symbol Lab, we can take a look at that one more time. All right, here we go. So let's take a look at the graph of the tangent of x. Oh, yeah, that's right. Look at all those asymptotes. So wherever that occurs, of course, the function is discontinuous, but it is continuous everywhere else. Okay, so it's only at those asymptotes that it's discontinuous. And so, as a matter of fact, the pattern here is at pi over 2. Let's go look at this again. It's hard to tell from this graph, but right here, this first one, this is pi over 2, which is approximately 1.7. And then this one is going to be, let's see what that is. 1.7 times 2. So, yeah, oh, pi over 2 is approximately 1.57. Sorry, 1.57. And then when we double that, it becomes approximately 3.14. And again, it's hard to see just by looking at this. But that's where it's cutting through. And then here, um, 3 pi sorry, 3 pi over 2 is approximately 4.7. And then it just goes on and on and on. So there's a definite pattern to the asymptotes here. So that's what this is getting at. At any point that does not fall into this pattern right here is a point where the function is continuous. Oh, there it is. They've got their own. Now, let's see. What does that look like? The sine of 1 over x. Let's try that one. Oops. Sometimes it's awkward to type into the symbol lab, but here we go. Oh, now that's not what I was expecting. Oh my God, look at that. That is very bizarre. Now you can see there's a horizontal asymptote, which means this function can never equal 0. But I don't see any vertical asymptotes. Now they're saying here that this function is not continuous at x equals 0, but I'm not really seeing that here. It may be that we just aren't close enough to it. Well, that's very strange. Well, I'll tell you. Oh, well, of course, there's the issue right there. You can't obviously have 1 over 0. So that would be the reason why the function would be discontinuous there. It's just that the graph doesn't really show that. But yeah, you can see why 0 would be disallowed here because obviously we can't have 1 over 0. So what they've done is they've broken it up into two pieces. It's a piecewise function here. So the function is sine 1 over x everywhere except 0. And when x equals 0, the function equals 0. So therefore, um, it's discontinuous at 0, but it's continuous everywhere else. Oh, there it is. They have their own picture of it. Now oh my God, multiplying by x, um, wow, look at that. So what they're trying to do here is use the squeeze theorem. They want us to see that x sine 1 over x is bounded between positive and negative absolute x. Let's write this down. And therefore, the limit, the limit as x goes to zero. Oh, I see. They did find this as h of x. Okay. So the limit, according to the squeeze theorem, is going to be zero because the limit for these two is zero. So because this function is always in between negative absolute x and positive absolute x, it has to have the same limit as these two. And so the reason why these limits are zero is because if you look at these graphs, you'll see that, oops, all right, it's not perfect, but you can see the point of it is that it touches zero, zero. So the limit as x approaches this point from either direction would also be zero. Now, this is the negative version. All right, that's slightly better. And again, we have this point zero, zero. So as x approaches zero from either side, we're going to reach a limit of zero. And so according to the squeeze theorem, since this function is always somewhere in between the two, at this point where both functions have a limit of zero, this one must also have a limit of zero. So rather than solving for it directly, we're using the squeeze theorem to prove it. Now, the intermediate value theorem, this is one of those theorems, you're going to run into it from time to time. And it's not always immediately obvious why it's useful. But the important thing is to understand what it's saying. So here's what's happening. You've got an interval of some kind. So we're defining a function over a specific interval, a to b. It's a closed interval. It could be anything. Let's say it's a to b. And so here's f of a, and here's f of b. So that now the important thing here is that f of a and f of b are different from each other. So as long as that's the case, and f is continuous, if we pick any point C in this interval, let's say here, then it must be true that this f of k, f of c rather, is in the function. In other words, it's part of the domain, the range rather. Okay. So it basically means there's nothing missing. You know what I'm, it's kind of they're just saying as long as the curve is continuous between the 2 points, um, over a to b, and as long as f of a and f of b are different from each other, no matter what point we pick in between, that implies that f of c is between f of a and f of b. Okay. And again, it sounds very abstract. You're like, what's going on here? Why do we need to know this? It comes in handy under certain conditions. And so one of those things you just need to remember it when you see it. Oh, here's the intermediate value theorem. Um, and there will be times when we can take advantage of it. But here it's enough to know what it means. So essentially, it's telling us that as long as the curve is continuous, whatever point we pick between A and B, f of that point has to be between f of A and f of B. Here's another one. This is their example, and it's a good one. So you've got A and B, yeah, and it's a closed interval. It's continuous across the entire interval. It doesn't matter what happens outside that interval. And f of A and f of B are different from each other. And of course, you can see just by looking at the curve, um, f of x is continuous between A and B. Or what I should say, to be more precise, over the closed interval A to B. So they've chosen this point C2, and this K is meant to represent f of C2. And we can see that f of C2 is between f of A and f of B. Oh, actually, sorry, I got these backwards. In this case, f of A is the larger number. So let's get these reversed. Okay. And now we're all set. Now, what they're also saying here is that we should be able to find two other points where this is true. In other words, um, K could be thought of as also f of C1 and f of C3. Okay. Um, in the graph I did here, I guess I didn't go over that. But anyway, that's what it's telling us. Well, actually, no, it doesn't guarantee that. That just happens to be in this case. Um, now that I'm looking at it, because it's a cubic function of some kind, that's why there's three of them. But in my example, that wasn't true. There's just the one case because it was rising continuously. That meant there's only one f of c. So, in other words, the important thing is that f of c is in between f of a and f of b. There might be others in there as well, but there's no guarantee. Okay, this here, it just because of the shape of the curve, there were three of them. But in general, this is all that we need. Now, oops, what happened here? It doesn't work in this case. Why not? Because the function is clearly not continuous over the interval a to b. Whoops. Okay. So therefore, if you notice, here's the issue. Here's K. There's no value in here that corresponds to it. Okay. It's sitting there. It's like an orphan. It's sitting there all by itself. It doesn't belong to any of the X's. And that's because of this discontinuity. So like I said before, something is left out basically. The K is not part of the range. Okay. Now, zeros. Now, this is something else you're going to spend a lot of time with. Zeros are what they refer to is the points where the curve crosses the horizontal axis. The word zeros, these are sometimes called roots, and they're sometimes called solutions. Okay. And so you can think of it as two ways. As far as the graph is concerned, these are points where the curve or the graph crosses the horizontal axis, or you can think of these as the values of x where f of x equals 0. Okay. It means the same thing, and that's why they're called zeros, by the way. Okay, so if whatever these x's are, if I plug them into the original function, they're going to give me a 0. Now, finding these can be very challenging, of course. And so here, what they're doing, though, is they're connecting it with the intermediate value theorem, where if the assumptions of the intermediate value theorem are met, um, oh, but only if okay, that was the key to the whole thing. It's not enough for A and B, f of A and f of B to be different. They have to have different signs. So here's our f of A, which is clearly a negative number, and here's our f of B, which is a positive number. So in other words, not only are FA and f of A and f of B different from each other, they have a different sign. It doesn't matter which is which. And of course, we have to assume that the function is continuous over the interval AB, the closed interval. And then what that means is, just like before, there's going to be a C in here somewhere, but specifically the C is such that that C is a 0. Okay. In other words, then there exists a C between A and B such that f of c is zero. Okay. In other words, c is a solution or a zero of f of x. Now, this can be very helpful, this kind of thing, because if we're trying to find a solution to a function, it's good to know, like, theoretically, if there is guaranteed to exist a solution in the first place, we don't want to waste our time looking for a solution that doesn't exist. So a theorem like this, because it guarantees us that there does exist a solution, can be very helpful because then, while we're looking for it, we at least know that it must be there somewhere. We just have to find it. If we don't know any such thing, we might be wasting our time looking for a solution that doesn't exist. So this would be where it starts to prove its worth, making it possible for us to determine if there's a solution of some kind. Okay, so now here's an example. We've got a polynomial, f of x equals x cubed plus 2x minus 1. Now, I'll tell you what, let's go to Symbolab and see what this thing looks like. Yeah, oh God, let's get rid of this. It's the ugliest thing I've ever seen in my life. All right. I don't even want to look at it. All right, what do we have? X cubed plus 2x minus 1. Graph. All right, here we go. Well, it's kind of interesting. Now, there is a solution here. It's not a nice number, it looks like, but there is a solution. Okay. It's kind of a flat. Sometimes cubic functions curve up and down, sometimes they don't. So it's kind of rising through the intercept here is, which you can tell from here. So they would like us to analyze the interval from 0 to 1. Let's say that that's 0 and 1. It's hard to tell from this graph but anyway, um, what we need to demonstrate is, first of all, this could be thought of as A, this is B. F of A is f of 0, -1. F of B is f of 1, which is 1 cubed. Let's move this down here. And that's going to be 1 plus 2 minus 1, which is 0. Huh. No, no, what did I do? 1 plus 2. Oh, of course. What did I? No, it's 2. What's wrong with me? It's 2. Shh. All right, that's better. Okay, so what we want then is some intermediate point, C, where f of C is 0. Now, I don't think they want us to actually solve for it. I think they just want us to prove that it exists. So we need to know that These two exist. They have opposite signs and they're different from each other. Okay. And then on top of that, the function is continuous. Um, Now, there's a theorem floating around somewhere in this book that explains to us that polynomials are always continuous, but I don't think we've run into it yet. So, but you can see x cubed plus 2x minus 1 just by looking at the graph. It's pretty clear that it's continuous. But anyway, so we know that the function x cubed plus 2x minus 1 is continuous, at least over 8, 0, 1, and therefore there must exist a c such that f of c equals 0. We don't know what it is. We can solve for it if we want to. It won't be easy. We can do it. But here, I think all they really need for us to do is demonstrate that it must exist. And yeah, well, okay. I guess that's all they wanted. All right, so here's an end of section example. Let's try it. Now, if you notice, it's hard to see it there. There's that little plus next to the 11, which means it's approaching from the larger numbers. So why don't we go into Symbolab and see what this thing looks like? Um, what is it again? 11 minus x and x squared minus 121. Oops. Ooh, okay. Now there's a discontinuity here at 11, and you can see why, because we can't have division by 0. Okay, so now if you look at the graph carefully, though, if you notice, if we approach from the left and the right, we're approaching the same point. Okay. And what we can do now, remember that theorem we had, which tells us that if two functions are identical at every point except one, the limit at that point is going to be the same for both of them. So what we can do here is this. Well, it just so happens that this function or this expression equals x plus 11 times x minus 11. And you can double check that with FOIL if you want to. So you've actually got here So if you now here's where it gets a little tricky. See, what they did was they made the denominator the negative of x minus 11. So that these will drop out, but we still have this negative 1 here. And so now we can substitute 11 in here without getting into trouble. Again, based on the theorem we had earlier, so we've got the original function, which has a discontinuity at x equals 11, and this version of it, which does not have a discontinuity. They differ where x equals 11, and in the second function, we have a limit of negative 1 over 22, which means that the limit up here must also be negative 1 over 22. Now, it's hard to tell from this graph because it's so tiny. It's very hard to see that it's just a hair below. Let me see if I can magnify this a little. Yeah, I don't know. It's still hard to see, but this is just, see, they're telling us that it's 11 comma negative 122, and so that's what we were looking for. Okay, so the correct answer after all that is negative 1 over 22. D. Yes, very good. Um, so now look at this one. Find the values of x, if any, at which it is discontinuous. Okay, well, obviously we're aiming for any values that cause division by zero. All right, let's see what we can do. Oops, we don't need, we're going to graph this in a second, but hold on one second. X over x squared minus 2x. So what we're going to do is set the denominator equal to zero. All right, let's do that. So we break it up into those two terms. If x times x minus 2 equals 0, that implies that either of those two being equal to 0 would cause the whole thing to equal 0. So those are the 2 points where we'll have discontinuities, x equals 0 and x equals 2. All right, so let's look at the graph. Yeah, here's another one. I'm not too happy about this one either. It's kind of strange. All right, x over x squared minus 2x. Okay. Now, as you can see, at 0, this is 0 over here, there is a discontinuity when x equals 0. There's also a discontinuity here where x equals 2. All right, so we got that part right. Now the question is whether the discontinuity is removable. Well, this one is, but this one is not. Okay, because at x equals 2, that's an actual asymptote. But when x equals 0, we're only missing a single point. So if we create a let's say, a piecewise function and define a value there, we could end up having a removable discontinuity. So also, if you look at this thing carefully, you'll see that up here, this one can be reduced to 1 over x minus 2 algebraically. So you can see that we can't allow x to equal 2 under any circumstances, but x can equal 0. It's 1 over negative 2. And so we have a removable discontinuity there. Okay, so yeah, it's um, when x is 2, because it's an asymptote, we cannot remove that discontinuity. When x is 0, we can. Okay. And so the strategy is what you're seeing here. What you would do then is you would say, well, the function is therefore not, no, sorry, for 0. And and this is how we remove the discontinuity by explicitly telling it what to do when x equals 0. Okay. All right. And that seems to be the end of 1.4. So 1.5, ah, infinite limits. Now, the properties of limits, so far we haven't seen any of these. All the limits were taken as x approaches a specific constant. But sometimes the limits can be taken as x approaches either positive or negative infinity. And so, for example, here, ooh, look at these. So this is the function 3 over x minus 2. Now there's clearly an asymptote at x equals 2. And it's not removable, obviously. But what they're telling us is that the limit as x approaches in 2 from the larger values coming this way of this function is positive infinity. In other words, if you notice, this curve is going up and up and up forever. It just continues to rise forever. On the other hand, though, if we approach it from the left, in this region, the function is heading towards negative infinity. It's going down and down and down forever. Okay. Oh boy. So you can see, and of course we can tell, and they're not equal to each other, therefore we have a discontinuity here, but it's an asymptote because the function never quite reaches that line, which means x equals 2 is not part of the domain. Okay. And yes, this is how we write it. If you notice, again, it's hard to see it there, but this is x equals 2 negative, meaning from the left. And that means as we move in this direction, the curve is heading towards negative infinity. And the plus, this one over here is 2 plus, which means that as we come here from the right, we're getting closer and closer to infinity. And that's, of course, referred to as an infinite limit. Okay. So this is the formal definition of what an infinite limit means. Um, Basically, as you get closer and closer to the asymptote, the function continues to either increase or decrease forever. Okay. So in other words, you can see this is the one where it's approaching positive infinity, and then down here, negative infinity. Oh, here's another one. So this one, you can see has clearly an asymptote where x equals positive 1 because we can't have division by 0. And so as we approach from the left, the function gets larger and larger forever. As we approach from this direction, the function keeps getting smaller. It's just the reverse of what we had a few minutes ago. Okay. So whenever there's an asymptote, you can expect to see this kind of behavior as we get closer to it. Vertical asymptotes. Now, we've kind of talked about this, but now they're going to formally introduce and define what we mean by a vertical asymptote. If f of x approaches either positive or negative infinity, as x approaches c from the right or the left, then that implies that x equals c is a vertical asymptote on the graph. Okay. So in other words, how do you know that it's an asymptote? Because coming from one direction, the function is approaching positive infinity, and coming from the other direction, it's approaching negative infinity. Okay, so we've seen that in these last couple of examples. And so that's how we know that this must be an asymptote. Oh, God, look at this one. We have two asymptotes. Now, the reason for that is because if you look at the denominator, it's a quadratic expression, which means if you set that equal to 0, there's two values of x where we have division by 0, -1 and +1. Okay. So if you notice, just focusing on the one, this one, approaching from the right, the function goes up to infinity. Approaching from the left, it goes down to negative infinity. And then for the negative one, as we approach from the left, now the function goes up to infinity. And as we approach from the right, the function goes down to negative infinity. Okay, so it's the same thing in both cases. It's approaching infinity or negative infinity, depending on which direction we're coming from. But that's how we can tell that these are asymptotes. All right, so they're giving us some rules. Now these are the same as what we had before, except that these involve infinity. So we're assuming that both of these um, are infinite limits. And oh, actually, no, they're assuming G has a positive constant. Okay. So then if we take the limit of their sum, well, it must be infinity because if you add a constant to infinity, it's still infinity. The difference, same thing. Actually, we can write it like this. Product. Oh, the product depends on whether L is positive or negative. So then here it's the same thing, except since L is negative, the limit then becomes negative infinity. Okay. And then the quotient, of course, is exactly now according to this. Now, if you notice, they've put G on top to make sure that we don't get division by zero. Um, so this is defined as zero because what's happening is that you've got a constant in the numerator and an incredibly large number in the denominator. So in the limit, this converges to zero. So it sounds strange, but that's how it works out. Okay. Well, what do they want us to do here? Oh, all right. Well, they're just, these are just examples of the same thing. Let's jump ahead to this one. Let's find this ex limit if it exists. Now you can see right away we have a problem because substituting 14 means that we're going to have division by zero. So why don't we look at the graph? Okay, so they're trying to get us to figure out what's happening at 14. Now, 14 is an asymptote. Okay, so therefore, now we're approaching from the right. So therefore, because of the way that you can see within the graph, um, as we get closer and closer, this would be infinity. If we were approaching from the left, it would be negative infinity. So therefore, it's A. Okay. Now what about this one? Oh my God, look at this mess. So once again, let's lean on symbol lab, x minus 1 over x. All right. Okay, now that's interesting. There don't seem to be any discontinuities except that it's in two sexual regions. So I guess This vertical line, the vertical axis that is, would be considered to be a vertical asymptote because they don't actually um, touch there. And then this line y equals x is a asymptote as well. Sometimes when you see an asymptote like that, just want to mention this as an aside. Okay, well, this is clearly a vertical asymptote. A horizontal asymptote would be more like this. Oh, see, I blew it there. All right, almost, almost. I'm so close. Let's try that one more time. I'm trying, what I need to do is show that it keeps getting closer and closer, but doesn't quite actually touch. All right, that'll have to do. That's a horizontal asymptote. And then this really bizarre case. This is called a slant asymptote. Okay. And that's what we're seeing here. So we got two asymptotes, one slant and one vertical. So what do they want to know? The limit as x goes to zero from the left. Okay. So we're coming from this direction. And you can see the function is getting extremely large as we get close to zero from the left. So that means the limit is just infinity. B. Okay. And you can tell just by looking at the graph. Well, what do you know? We're done with 1.5. So chapter one is completely done now. Now, of course, that means that we're done with limits up to, well, we're not going to completely stop seeing limits, but the next chapter will focus on derivatives. But in the early part, you'll see that the reason why they're doing it in this order is because derivatives themselves are defined in terms of limits. So we have to start with limits and then we'll see how they apply to derivatives. But once we've done that, then we can go ahead and learn a bunch of rules that will make it a little bit simpler for us to find the derivatives that we need. So in the beginning of chapter two, there'll be some limits again, but they're only used to help us understand what derivatives actually mean. And then we'll start learning a bunch of rules that tell us how to calculate derivatives. Okay. So again, it is really maybe the most important chapter in the whole course. So it's very important to say the least. So we'll save that for next time. And then that will be chapter two, our first look at derivatives. So I'll see you then.